Okay, so we are looking at the significant figures and we just now brainstormed about who uses these numbers. So as many of you pointed out that the numbers are being used by the scientists, like all kinds of scientists, and scientists can be, the chemists need numbers in a certain, for a certain like chemical project. Biologists are going to look at it differently than physicists are similarly using numbers for calculating the physical situations, formulas, then all kinds of researchers. And this also includes the researchers who are like a social scientists also. So even in the social science field, people who are trying to gather data on the societies, on the people, on the economics, the supply and the demand and the cost of the stocks of the companies. Do you guys know some story behind the GameStop, the GameStop stock?
I heard about that. Also, military people, because like they need to fire the artillery correctly.
Absolutely, military, yeah, army, military, all the defense personnel use numbers, and nurses. And then similarly nurses, it's very important for the nurses to know exactly how much the solution should be made, or like what is the prescription. Pharmacists, all those people in the medical field, very important. They can't fool around with the numbers there. Why? Because let us say a doctor said that this individual should be given 23 milligrams of this particular medication and 4 times a day, right? And instead of looking at, let's say, a nurse misunderstands or kind of like doesn't pay attention to it. So instead of 23 milligrams, she gives it 23 grams 4 times a day. Now that's going to kill the patient, right? So that's why it's very important to have that sense for the numbers and the sensitivity and understanding of the numbers. Okay. So all these people are taking numbers, work with the numbers, even if it's the chefs, not just doing the exact calculation, but also have estimating so those things. Now here's the thing, with these numbers there's something called accuracy, and there is precision. Okay, so accuracy is, as the name says, accurate. Precision. Okay. Precision and accuracy. Okay. They go hand in hand. You would want your data to be both accurate and precise. Your measurements, when you're measuring things, or even if you, especially with regards to measurements, your data should be accurate and precise. Now, accurate means when the numbers, your results, when you're doing the calculations, you're taking the measurements, they should be close or should match the real value, the true value. Okay. Now, what is a true value? Now, here's understand this. True value is the known value, known known value. And true value, known means, like, generally, see, here's the thing. You guys are doing these reactions in online here, unfortunately, but if you were to do these experiments in the lab, then the knowns are made by the lab technicians, and those are like stock solutions. And then we make unknown samples and we give to the students to look, to carry out to certain experiments and come up with their results. And then we match the results with the true values, the known values, which is the, data on the whatever, you're trying to assess, which is known to the lab technician. So if the student's data matches with that, what the lab technician has in the lab, then that means the experiment was successful and the student did the right things. Okay. But if the data is not matching, then that means that the student made a mistake. So this is how we work in the labs. So true values are not just the values which are made, which are of the solutions made by the, or the objects that are provided by the lab technicians. True values also mean the values which are known online, right? Known through the Google searches. Let's say, for example, you're trying to determine the density of an unknown sample, and it comes out to be 2.7 grams per centimeter cube. And so the known value of this is already listed, like, okay, which of the elements have the known values? which of the elements have a certain this particular density, which is equal to this particular amount that, so if it matches, that means your results are accurate. You did the right thing. Okay, so accuracy, you want the, and precise. Precision is every time you repeat experiment. Generally, when we conduct experiments, there are 3 or 4 steps. So when we conduct these experiments in 3 steps or 4 steps, we find that we get the same data. Now, sometimes this happens, you may get the same data over and over and over again, but it may not match with the known values. It may not match with the true value. Even though you're repeating it over and over again, that means there is a mistake in the steps. What is that? Is the camera zoomed in? Mm, I don't know. Okay, just a minute. Let me just see. There was a comment. Your camera has zoomed in and it's blurry. I don't know.
Is anyone else experiencing that? And oh, there, it flipped back. You
Okay.
just fixed it.
Oh, I don't know.
I think we can zoom in and zoom out the professor pictures, and also the work she doing. We can zoom and zoom out.
You can zoom in and out on that. Your students can do it.
Yeah, we can do that.
Oh, good. Okay. Okay. So that's how, yeah. So the students can do it actually, zoom in and out. Okay. So anyway, so let's do this thing now. So precision is trial based. So if you try to do these experiments and you're doing these experiment, trial 1, you get some result, trial 2, trial 3, trial 4. And then if you keep getting the same results, but they do not match with the known value, that means that your data is precise but not accurate. On the other hand, you may get all these different results and it may not match with the true value. That means neither precise not accurate. So this is how, we when we are conducting experiments, we gather data, we kind of assess whether this data is good or not, whether the results are good or not. Okay, so now we're going to just show it a pictorial representation. Okay, so this is the true value in the center, and outside are these, just to imagine, like, these different data points in this region. So your result should be, if your data is right in the middle means this is the true values. If it's exactly matches the true value, that means it's precise and accurate. So it should match this, it should be same. So in this case, the data is precise as well as accurate. And accurate. So this is what you want, precise and accurate. Okay, so trials are driven by the precise. But if your data points are lying, here outside, not even near the true values, that means that they are not accurate, obviously, and your data is not it's far away. See, they're not the same. So they are like, one of the data is here like that, one of them is here, one of them is here. All these data points, all these are not precise and not accurate and not precise. But on the other hand, if you have some of the data points which are like all bunched up, every time you try, they come close to in the same value. And in that case, they are precise, but not accurate. Okay, so this is like a pictorial representation of what we talked now. Okay, next, let's look at now. Okay, people taking numbers, right? We're working with the numbers. People are working with the numbers, and we find that everyone gives value to a number. And obviously the value, it varies from people to people. Like, for example, here's one example I'm telling you. Look at a banker. Okay, when you do the calculations, or anyone, even the people who are in the taxation, people who are accountants or people who are in the finance industry, any one of them, any one of these people, for them, only two places after the decimal have a value. If you look on your what is it called, the calculators, you find that there are several numbers after the decimal. So for people who are bankers, tax people, or the accountant, those are useless. Only two places after the decimal have value. Okay, decimal point is value to them, is important, is significant, in other words. Okay, is significant. Now let's look at someone who is a chef, or people who are like, chefs, tablespoons. Now, come on, we've all seen it. These tablespoons can vary in size, right? Some of them could be bigger, something could slight. So there's no exact measurement. Sometimes when they are just, estimating. So chefs generally estimate. So a little bit here and there is fine. Their exact measurements are not very exact. Okay. So for the chefs, it is just estimation. Estimation. Now in the estimation, they can use tablespoon. They can even use hands. When they pour things, they just use this. I mean, just use like a little pinch of salt, right? And when they use a pinch of salt, it's like not exact. So for them, estimation is important. So for, let's say, for example, they want to make a food for 113 people. Like 113 people are coming for a party, and a chef wants to make a food. So he's going to an estimate. For him, in his mind, 100 is better than 113, although it's less, right? So 100 gives him like an estimate of how much of the food he has to prepare, and then the rest of it is just he's ballparking, right? So these 100 gives him, like, quickly he can do the math. So for him, this 100 is significant. Okay, you see that? So for tax people, two people, or these bankers and all financial people, two places have the decimal. Now let's look at somebody who is an engineer. Now those people like to be very precise, be very exact, So for them, certain places after the decimal, certain places after the decimal are important. Yeah, so certain places after the decimal are significant. Okay, so for then how much, how many, now that is determined by, how much of the uncertainty can they tolerate. Okay, so there is a concept for engineers, very specially, and scientists also, the concept of uncertainty. Now uncertainty means certainty. Now zero, so plus minus 0.01 plus minus 0.001 plus minus 0.0001. How many places? 0.0001, so that means that these, if it depends what kind of measurements they are doing. So for them, for a scientist, he has to have these numbers one place after the decimal, but he can do away with, he can tolerate if this is not one, if this is two, or if it's like 0.9, it's tolerable for them. Similarly, this digit, this place value, this place is kind of like he can tolerate ups and down. So think about it this way. You guys go in, like, let's say a grocery store, right? You've all purchased produce, right? You put the produce on that thing, that weighing scale they have, right? Don't you see the finger, the needle? It moves up and down, and then it kind of like just moves, and then it stabilizes, and then it slowly stabilizes, and then it will point in that little space that is like nothing is written there. You see that? Like if you have seen it, this is that scale. And in that scale, the needle is going to point sometimes in between this empty space, right? So what is that? What does that empty space mean to you? You guys tell me. What does this empty space mean to you? This space.
Like halfway between the two numbers on either side.
Right. Two
There's
numbers.
uncertainty there. There's
They-
uncertainty unless there's a small dots you can read.
Right. Unless there are small dots that you can read. But here's an interesting part. Even if it's the small dots, sometimes the needle can even point in between those small dots also. So there's always going to be some uncertainty. Whenever you're taking the measurements, there's always going to be some uncertainty. Because there's always the way we, our scales are designed. You take a thermometer, look at a thermometer. There's always going to be that little space that is just blank, empty space in between the two lines. Okay, weighing scale, same story. In between the two lines, there's always going to be, even if the lines may be very, very close. Okay, now not only that, digital weighing scale. Digital weighing scale does not have these lines, but digital gives you the reading, right? But here, even in the digital weighing scale, you will see the last number runs up and down. So this last number, the last number is the ones that's running up and down. That is where the uncertainty is. And that's, it depends who's doing the measurement and in what context the measurement is being used and how sensitive the individual is to the uncertainty. Like, think about it. People, especially these folks, I mean, three people actually. One is the nurses and all the people who are in the medical field. For them, precision is very important. Accuracy and precision is very important. For example, people who are like here, rocket scientists, people who are, I'm going to just put it, people who are in the construction industry, they just cannot go do away with uncertainty. Business people, fine, little bit loss and loss here and there. Classroom, my class, 25 students. I said, okay, fine, I can take 30 students, So kind of like the college is very sensitive about no more than 25 students, but I'm like, doesn't matter, it's okay. So I kind of like take that. So 30 students in my class here. Dietitians can similarly play around with a little bit of the numbers, but similarly, we can't fool it. Rocket scientists or even, people who are like any kind of engineers, they cannot fool around with numbers. For them, certain digits after the decimal are like absolutely important. Medical field also, construction. If you make a wrong, like people who are like, for example, the social scientists, right? The social scientists, it's okay, how many people are, the demographics, who are people who are, doing statistics, those people cannot be very sensitive, it's fine. But if you look at the people who are data science, the doctors, engineers, and these two people, very specifically for them, that uncertainty, how far they can tolerate an uncertainty, that is like very important, very critical piece. That is why we have significant figures. Okay, so here, what are the rules regarding the significant figures? Now, some rules, and generally, here's another thing. Significant, if we can, figures, they apply to measurements. Okay, significant figures apply to measurements. Now, what are measurements? Whenever you're doing measurements, significant figures are used. And that is to do, because of this uncertainty, we're trying to address that, or we're trying to keep the uncertainty to the minimum. Okay, so now the question is significant figures, and in the significant figures, when we talk about measurements, they are used especially wherever there are measurements are involved. So now comes the question, measurements and calculation. What is the difference between measurement and calculation? What do you know about that? What do you know about measurements and what do you know about calculations? And what is the difference?
Measurements are directly recorded, but calculations, you have to figure it out from other what you do know.
Right. So measurements are recorded using some kind of measuring devices, right? So here measurements are done on apparatuses. And when you say apparatuses means you will have to take a reading. And when you're taking a reading, that's another thing. Whenever we are taking readings, the possibility is we might introduce some errors. Okay, so let's say, for example, a tall individual versus a short individual. Both of them are taking the data. Both of them are reading a barometer. One is going to look from the top, the other is going to look from the bottom. You see that? That's where the discrepancy comes in gathering the data. That's one thing. You are reading these numbers. Again, we talk about this uncertainty. Whenever somebody who is like, let's say a scientist or an engineer is using a measuring device, let's say a measuring tape, and he's trying to measure, let's say a construction worker, he's measuring like how much should the door be in a room. You know, he's trying to put a door or a window or something. So they use these measuring tapes. Right? So when they use the measuring tapes, and once again, they have to deal with this uncertainty of, okay, up till now, this is measuring like so and so numbers, but after that, I'm not sure because there's like a blank space on the measuring tape. You see that? So that's where the uncertainty comes in, and that's where the rules regarding the significant figures are used. So when we use measurements, we are looking at, let's say, thermometer. Even in the thermometer, the scale, you know, that scale and that scale, the lines between the lines, that weekend lines, that's where. So let's look at these. And when we do the calculations, basically calculations are just mathematical, you know, rules, just mathematical rules. You know, how do you divide, how do you multiply, those things. And they're also based on formulas. In chemistry, in physics, you know, we used a lot of formulas, so that's what it is. So okay, now let's look at the significant figure rules. So number one rule is that the non-zero numbers are significant figures. Okay, now for example, a non-zero number is just give me 1 minute. Okay, let's say, for example, you have 25.3 grams. Okay, so here 25.3 grams. How many significant figures?
3.
3. Very good. So 3, that means that when you are measuring something, one place after the decimal and 25, these 2 digits before the decimal is important. Okay, so this is next is, let us say you have another number 3429.623. How many significant figures?
7.
All of these numbers are important. Yeah, 1, 2, 3, 4, 5, 6, 7. So this becomes 7 significant figures. Very good. Next is the 0 in between the non-zero numbers. 0 in between non-zero numbers. Okay, so 0 in between the non-zero numbers is like, for example, 2, 0, 3, 4, 0, 6. Okay, so in this case, we will see that the number that is here, 1, 2, 3, 4, 5, 6. So 0 is counted. So this is another commonly used, you know, significant figure also means like how many numbers should be counted or are important for a measurement or for a calculation and should be counted. Okay, or included in the measurements. Okay, so here we will have 1, 2, 3, 4, 5, 6. So 6 significant figures. Now let us say you have 5.0, 0, 3, 2, 0, 1. Look at all these places after the decimal places. But, you know, so 1, 2, 3, 4, 5, 6, 7. All of them are important. So counted. So this is 7 significant figures. Next, let's look at the 0 that is n. Now, anytime, now keep this in mind, anytime you have a decimal, that 0 will be counted. Okay, anytime there is a decimal, so count the 0. So the 0 that is end of the decimal point is counting. So 0 at the end of the decimal, 0 at the end of the decimal, and before the decimal also actually. 0 at the end of the decimal is important. So this is, let's put it 1 here. Like for example, you have this number 3, 4, 2.00. Okay, so these, even though like this is just because there is a decimal, this is important. Anytime there is a decimal present, that means this 0 is important and this one is also important. So that means you need to go 2 places after the decimal and just make sure that when you are measuring something, it should be just 0, 0, not more than that. So, and you know, so 1, 2, 3, 4, 4, and 5. So this comes out to be 5 significant figures. Okay, next is, let's say 0 at the end of the decimal. I'm going to just do a few more. Like for example, 25.0. So this is 3 significant figures. So these are important. Again, 1, 2, and 3. So this is 0 at the end of the decimal. Now let's look at if there is a 0 in front of the decimal. 0 in front of the decimal. 0 that is in front of the decimal. Like for example, 50 point. If it is written like that, that means no number after the decimal, just exact 50. This is what it means. So here the number is, these 2 are important. So this becomes equal to 2 significant figures. Okay. Next is in the coefficient of a number written in scientific notation. So if there is a scientific notation, numbers that are written in the scientific notation, scientific, SCIENTIFIC, scientific notation. Okay, so in that, all of them are important. Like for example, 4.8 into 10 to the power 5 meters. So in this case, we are going to not count this 0. This one is not counted, but the ones that are counted are these 2 figures are counted. So it comes out to be 2 significant figures. Okay. On the other hand, if you have this number like 5.70 into 10 to the power -3 meters or grams, sorry, grams. Okay. So in this case, you are getting this, and this. So once again, the exponents, the 10 to the power, whatever exponent is not counted. So this one, oh, sorry, this one we leave, but we are going to count these 1, 2, and definitely 3. So, you know, anytime you see a decimal point, just count whatever zeros you see. Okay, so this is 3 significant figures. So this was if there is a decimal. Now, okay, next is, fine, if there is a decimal, but I'm going to put it here, Ruti. Zeros that are, again, if there is a decimal, we're looking at that. Zeros in front of the numbers. Not 0 that is in front of the decimal. That one is counting. That is counted. 0 in front of the decimal, counted. Scientific notation, counted. This one, 0 at the end of the decimal, counted. Zero in between the number of non-zero counted. And similarly, the last one, non-zeros are all counted. But now comes the zero that are in front of the number. These are not counted. Not counted means not significant figures. All right, so now we have this number, for example, 0.0004 seconds. So in this case, all these numbers that are in front, even though there is a decimal, they are not significant figures or not counted. So there's only one significant figure in this case. So these are dropped. So, I mean, in a way they are important, but they are not important like when you are doing the calculations that relate to significant figures. So these numbers are basically like, yes, this is important. They tell you like, okay, 1, 2, 3, and 4. So the same thing can be written as 4.0 into 10 to the power -4. But that's the only value the zeros in front of the number have. They help you to write the number in the scientific notation, but we consider them to be non-significant. So they are like dropped, but it's not like they're just randomly dropped. Look at another example, 0.075 centimeters. So in this case, you are going to see that these two are not significant figures. So only two significant figures here, these two. Okay, so pay attention to it. Decimal, yes, decimal zeros are counted, but if they are in front, then they are not counted. Only the front of the decimal. Front of the number. Okay, next is the exact numbers. Next is the exact numbers. Next is and now here comes the exact numbers. Now exact numbers are the numbers that do not have a decimal. So the exact numbers are the numbers that do not have decimal. Or, I mean, generally decimal is present, but it is just implied decimal present. Implied decimal is present. Okay, like for example, you have here this number. Let's say, for example, 1, you have 10, you have 100, and you have 1,000. Now, just because someone says that, here the numbers, non-zero numbers are these numbers 1. Okay, so here, yes, this is one significant figure. All of them will be one significant figure because they are non-zero numbers. But in this case, two significant figures. This can also be two significant figures because this is 10. This can be two significant figures because this can be written in scientific notation, but in reality, there are actually 3 significant figures. Makes more sense. So this one here, 2 significant figures possible. Okay, 3 significant figures are also possible, and 4 significant figures are reality. So 1, 2, 3, 4. So in the real sense, yes, this is one significant figure, 2, 3, and 4. That makes sense. That 0 has added value to it. Think about it. If somebody hires you for a job and they give you $10 versus somebody hires you for a job and they give you $100 versus someone gives you a job and they give you $1,000, where are you going to work? 1,000.
1,000 over the 10,000, because if it goes up another notch.
1,000.
No end to it. Yeah. So the thing is, so you see that in your eyes, that 0 has a value, right? That 0 has importance. That is why you said, no, I'm going to work for this guy who's giving me $1,000, right? So for you, all those zeros are important. So that is why when we are looking at the exact numbers, these exact numbers have variable significant figures, because the scientists can write this number, this number, this number in scientific notation, right? That can be written as that. So that is why for the variable significant figures. So therefore, for the most part in the calculations, we do not count the exact numbers. When you're doing the calculations for significant figures, we don't count the exact numbers because it's variable significant figures, okay? So this is one thing. Now let us look at these rules regarding the significant figures when the calculations are done, okay? So first of all, the rounding up and rounding down, and always keep this in mind, that keep this in mind, whenever we are doing these rounding numbers, so keep this in mind, that when you're up and down, so in chemistry, we don't round down. Why? We do not round down in chemistry. Why?
So we don't get too little.
Yeah, okay. That's one thing. Besides that, okay, the thing is, we don't round down. Rounding down means you are cutting on the data, right? You're cutting the data. Now, we in chemistry deal with matter. Matter is anything that has mass and occupies space. Matter is anything that has mass and is occupying space. Now, here's the thing. Let us say I have this pen. The length of the pen is 10.1 centimeters. So what will you write? 10.1 centimeters, right? You're not going to round it down to 10. Does that make sense to you?
Yeah, because you can't destroy matter.
Right. Matter cannot be destroyed. That means you're cutting the matter. So that mass, you can't just say like, okay, it is 10.10 centimeter because yeah, it should need it to be rounded down. No. So in chemistry, don't do that. Yeah, in other subjects, I mean, in science, physics, biology, chemistry, don't no rounding down, because physics, we are all studying the physical properties of the substance. And if the physical property comes out to be, let us say, the boiling point of the substance is 100.4 degrees Celsius, then that is what it is. You don't take it like, oh, it should be 100. No, that's where the difference between, measuring and calculation is. In calculations, ideally in chemistry, you shouldn't round down even in calculations. You should not. It's only when you're estimating, then it's fine, okay? So matter means, because of matter, here's a very important piece here, do not round down.
What about rounding up?
Rounding up, not a whole lot, but rounding up is kind of okay. Why? Because here's the thing, we are dealing with matter, and we are in that matter, we have kind of estimated that there is 1 mole, and there is 1 mole contains 6.022 10 to the power 23 particles, and the weight of the atoms, and those weights of the atoms, we have, because they're all of them, if you look in the periodic table, these weights of the atoms are with the decimal points. So to begin with, anytime there is a decimal point, there is going to be some ambiguity is going to be there, little bit of it. Now, even in the atoms, the weight of the atoms, you look in the periodic table, the weight is average of the isotopes, and we will study this further. So average of the isotopes includes the abundance factor, and abundance factor, again, there is some ambiguity there. There's some estimations, are also used. So the numbers you see on the periodic table are the numbers we are going to use to do the calculations throughout, all kinds of calculations. So therefore, it's okay to round up like a little bit, it's okay to round up, to the, so for the most part, Okay, sorry about that. So for the most part, 2 places after the decimal are considered. 2 places after the decimal are considered to be okay. So when you're doing calculations, I'm going to write this down. So whenever you're doing calculations in chemistry, so whenever you need to round up, generally rounding up is done, and 2 places after the decimal is kind of a standard for the answers, for rounding up. So keep it that way. Now let's look at some of these numbers, which are, and also rounding up and rounding down. Here's another thing. The rule regarding the rounding up and rounding down is driven by, the significant figures only. So, okay, let's look at, first of all, rounding numbers. Okay, let's say you have this number 8.4234. So you know one thing, that round up is if the number that you are retaining, the number that is retained, let me put it somewhere here. Okay, the number that is retained, what do we do with that? So status of retained number. Okay, so the number, if the number you are dropping off, the dropped off number, if it is 5 and above, okay, so what happens to the retained number, the number you want to retain? It is rounded up by 1 digit, okay. But if it is like 4 and less, then generally round down by 1 digit, okay. So that's one thing, but like I said, be very careful with the rounding down. We will prefer not to. Okay, now let's look at this number. For example, 8.4234, okay, and you want to have, let us say, 2 significant figures. 2 significant figures. So 2 significant figures in this number would mean that we want to keep 8 and we want to keep 4. But 2, these guys are going to be dropped off. And when we see that 2 is less than 5, therefore the number is just going to be 8.4. Leave it as it is. So in this case, I would say round down by 1 digit is kind of like, 1 second, let me see. Yeah, so 2 significant figures. So in this case, just keep as it is. Keep as is. For chemistry rule is that keep as is. Generally, if in other scenarios, math, you round down, but we don't. So I'm going to put a note here. Do not round down. But what you should do, you should instead keep that number as it is. So that is why in this number 8 and 4, it doesn't become 3 or whatever. So it's just 8.4. All right. Next, yeah, go ahead.
The question. I thought after the decimal we were supposed to keep the two numbers after the decimal were significant. So I probably would have kept it. I would have probably kept it as 842 because I thought we're supposed to keep the 2 numbers after the decimal.
Yeah, but here's a question. If the question is asking you calculate the answer up to 2 significant figures, this is what you're being asked. So you keep,
okay.
So pay attention to what, the question is, if the question wants you to keep, calculate up to 2 significant figures. So let us say next question is, this is one. Next question is, let us say they're saying that 3 significant figures. 3 significant figures. Get the answer up to 3 significant figures. And the same, same 3 significant figures is what you want in the final answer. And here is this number given, 8.4234. Okay, so you need the 3 significant figures. So now 1 is important, this number is important, and this number is also important. So these are the 2 you're going to drop.
Okay, perfect. Thank you. I understand.
Yeah. And so this is 3 is less than 5. Therefore, you keep as is. Don't round down. So here you would keep it 8.42, and that's the answer. Okay, so this is one thing. Next thing is, let us choose round up. Let's see, 3 to 5, 6. Okay, let's see this number. See, this is 3, 2, 5, 6. And the question is saying that get the answer in 3 significant figures. So this means you need this number, you need this number, you need to retain this number, but this number is going to be dropped off. And when this number is being dropped off, keep this in mind, 6 is more than 5. Therefore, we are now going to get 3, 2, and 6. So 5 plus 1 is 6. So this is how your final answer is going to be. Okay, so 3.326 is the final answer. Okay.
Wait, I thought it was like a 260 because it's a whole number.
Wait 1 second. Drop 6 and increase the last retained digit by 1. So this would be, oh yeah, that doesn't make sense also. Yeah, you're right about that. Sorry about that. Okay, here you have dropping of 60, and then this one is increased. The 5 is increased. Let me just remove this. Sorry about that. Okay, so 6 is being increased by yeah, so this would become 3260, and 6 is more than 5, so 5 is increased by 1 number, 6, that is 6. And then, yeah, and then 6 is the one, even though you drop it off as a number, but that place value still stays. Yeah, the place value, retain the place value of that number. Yeah, otherwise it won't make sense. That's true. Okay, so this is one. Let's look at another one. 3, 2, 5, 6, and here you want 2 significant figures. So in this case, yes, you retain the place value. This is the point I forgot to mention here. Retain place values. Okay, and that's especially for exact numbers. For exact numbers. Yeah. Okay, so this is the exact number. Again, exact number. Yeah. Okay, so here we have 3 to 5, 6, and we want only 2. So we want this and we want this. So we are going to be dropping off 5 and 6, but we will retain the place value of this. So 5, 6 dropped off, but 5, it's because it's 5. Therefore, what does this become? 3, 3, 0, 0. Because, oh, thank you. Okay, so this 5 is increased by 1, and 3, like 5 is, increased, and 2 gets increased by 1. So that's how this is 3, 3, 0, 0. So keep this in mind that for the decimal points, it's okay to drop off these numbers. That was the thing. It's okay to drop off. Anytime you have these decimal points, it's okay to drop those off. But if there are, similarly here, we drop these off, these guys, you know. So in this case, but if you have exact, you retain the place value. Okay.
I have a question.
Yeah.
So if it's an exact number and you round up, you add zeros for the two place values?
Yes, yes. Yeah, because see, here's the thing. If we do it 3, 2, 5, 6, and fine, we only need 2 significant figures. So this becomes 3, 3. But the value of this number changes, right? We cannot, we need to keep the value of the number. We like the place value, you know, those. So these have significance, these have importance, but it's just that we are rounding them up. So we are kind of like, we need to retain, we need to retain the place value. So in this case, we are going to keep, this becomes, and this, their space is, their place value is still there. So 3000, if this number is in 3000's range, this is 3000. Otherwise this becomes 33, and that's loses the value. It's not, it doesn't make sense. Okay.
Yeah, got it. Thank you.
This is not like little bit, it's kind of implied in the book, not very clearly explained, but that's okay. Now let's look at these digits, rules regarding the significant figure, like relating to calculations. Okay, calculations. Now, in calculations, you do additions and you do subtractions, right? In calculations, you're doing additions and subtractions, and you do additions, subtractions, and you are doing multiplication, and you are doing division. Multiplication, division, addition, and subtraction. So here's a rule regarding the addition and subtraction. Addition and subtraction, you will have, let's say, a decimal point when you're adding. So in that decimal point, you're going to count the places after the decimal, places after the decimal. And your final answer is going to have the decimals that are, final answer will have the lowest decimal place. Final answer will have the lowest decimal place. Okay, and multiplication and division, you count the significant figures. Count significant figures of all the questions, of all the numbers that are being computed. And your final answer will have the lowest significant figure. So these are very important pieces here. And another very important one, never round up or round down in between the steps. So you only round up. Like I said, don't round down, but you'll have to keep things as it is. But here, only round up, which the final answer. Only the final answer is rounded up. Okay, so now let's look at these examples here. So you are given this number. Let us do the study check problem, page 34. And here you have a study check 2.4. So this is not done for you, and we'll do it. Okay, here you are going, perform the following calculations, multiplication and division. Okay, here, 45. So this is A. 45.26 multiply by 0.01088. So here is a multiplication and division. So here we will see that in multiplication and division, we look at the significant figures. So here there are 4 significant figures. And in this case, there are 4 significant figures. Everyone agree with that?
Yes.
Everyone? Okay.
Yes.
Yeah.
Yes.
Good. So your answer should have 4 significant figures. Okay. So let's do the multiplication. You guys tell me what is the answer?
Professor, can you scroll it down just a little bit? I missed that top part.
Oh.
Ya terminó el descanso.
Si no nos había dado descanso.
Is it 0.492?
1 minute. My coffee. Okay, it's 0.492.
490. It's in 490.
There should be more. Remember,
0.4924.
right?
Yeah.
This is
4288.
So 4 significant figures.
¿Mm?
So when you do this number,
Después miro la grabación, lo está grabando.
go ahead.
¿Está grabando?
Hello, Micah, you're raising your hand.
Well, I was about to answer, but like,
Oh, yeah.
we got answered, and I just realized that my original answer was 4.492, but I forgot that 0 doesn't count as a figure, so I had to add the next one.
Yeah, yeah. Good. Okay, let's do another one. So let's do part B. Now you guys do this with me. 2.6, okay, divided by 324. Now, one thing, how many significant figures, first of all, here? 2.6, how many significant figures?
2.
3.
2.
Yeah. So these
2.
are 2 significant figures. What about this guy over here?
3.
3.
And remember, this is an exact number.
1, 2, or 3.
Yeah. So exact numbers have variables. So that is why we don't count.
Cargaba aquí Rodrigo Papi.
We do not.
Eso era para poner el fracture.
¿Y lo tiene él, pues?
En la placa ahora.
¿Ah?
I'll have to. Okay, guys. Sorry, there were some background noises coming. So, so we have. So I have unmuted. I've muted everyone, but you guys unmute. You say the answer and mute. Okay. 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 Anyway, so exact numbers, variable. Therefore, we do not count them. So your final answer in this case should only be 2 significant figures.
Yeah.
Okay. So now do it. Tell me what you get.
0.08.
So I did the division, Ms. Sharma, and I got 0.0080, but my final answer in sig figs would be 80.
Yeah, 1 second. So 0.0080.
80.
Okay. So when you do that, your final answer is, okay, here's the thing. Your final answer, it can't be 80. Your final answer is still going to be this, but you know, these are not counted. So it doesn't matter. These zeros, you know, these 2 zeros are not counted. Your final answer will be, yes, 80. But 0.00 will still be there, because remember that 0.00 can also be written as 1, 2, 3. So 8.0 into 10 to the power -3. So this way, yeah, this is a better way of showing it. So this is just a standard notation, standard form, and this is the scientific form. Okay, scientific. So in both the ways, we will have two significant figures. Okay, so these three zeros are not significant figures. All right, next let's look at this type of problem. Okay,
Question. So
Yeah.
that would be written out 80. Would you accept that?
no, there is a difference between, okay, think about it. There is a difference between this number and this number. Yes or no? Yes,
Yes. Yes.
right? This is 80
Yes.
is a big number and this is a small number, right? So so what you guys should do is like look at it. So this number 0.0080, it means it is a small number. It's a very small number actually. And that number, and then like what you're saying is 80, they cannot be the same. It cannot be equal to 80. So writing the answer like 0.0080 is the right answer. Why? Because this still is these are the two significant figures and these are not. These are not. So it doesn't matter. The zeros in front, in other words, are not like counted, are not important. But this number,
So just like highlight the 80 as two significant figures.
yeah, you can do that. Or you can show the way I have written.
Okay.
Is it better to write the scientific?
That is in fact more appropriate actually, because it's clearly showing you two significant figures right here. You see that? It's more clear that way. Okay, let's look at another example. The C, and that is 4.0 multiplied by 8.00 divided by 16. Okay, so how many significant figures here? 4.0?
2.
2.
How many over here?
3.
3,
3.
Very good. And how many here?
2,
2.
Yeah, ideally like two significant figures, but because it's an exact number, so it's not like exact numbers are not included in the calculations like for significant figures. So your final answer should have how many significant figures?
2.
2. Significant. Okay, now you guys do the calculation. 4.0 multiplied by 8.00 divided by 16.
Two.
0.0.
Right, because we need two significant figures. So fine, even though the calculator will say 2, but you need to account for two significant figures. So it's okay to write 2.0 because it's 2 showing two significant.
Okay.
So the more practice you guys do, you will get it. But I did these for you. And then there is a worked example that are also done, which you should do when you do the extra credit. So that will, help you. So this one was, I did this, which one was this? Yeah, 2.4 page. So this is the study check problems. Okay, now let's do the next one. Okay. Next one, addition and subtraction. So the rules regarding the addition and subtraction is, okay, the rules regarding addition and subtraction is that we would need the lowest decimal point in the final answer. Okay, decimal point in the final answer. Okay, now let's look at this problem, 2.5, problem to study check, 2.5, and this page 35. Okay. All right, significant figures in addition and subtraction. So let us save 2.5, page 35. So you have to perform this. Okay, let me write this down. 82 point, let's just put this properly here. 82.45. This is one. Then comes 1.245. Then comes 0.00056. Okay, and this is milligrams. This is milligrams. This one is milligrams, and this one is milligrams. And this is divided. Okay, now they are saying add. So here we are going to look at the places after the decimal. So this is 2 decimal place. This is 3 decimal place. And what do you think is the decimal place of this one? Tell me. How many decimal places is the last one?
2.
1 minute. Alicia Grant. Raise the hand.
Oh, it's okay. We can solve this and I can act it afterwards.
Oh, okay. Okay. Okay, you guys tell me last one. 2 is, okay, not the answer. Remember the rule. Anytime you have a decimal point, where did it go? Decimal. So the 0 at the end of the decimal points are counted. 0 which are in front of the decimal points are counted. And zeros then are in front of a number are not counted. Okay, so zeros that are after the decimal point here are counted. So here's your decimal point. And so these numbers, this one, so this is counted. So 1, 2,
5.
5. Yeah, 5 decimal points. Okay. So the decimal place, you know, it has a decimal point has a, like it gives value to the zeros. Okay, so now add. So this is 6, this is 5, this is 5, this is 9, this is 6, this is 3, and this is 8. Okay, so the question, the final answer, you should have how many places? Remember the lowest, yeah, lowest decimal point. So this is the lowest decimal point. So your final answer should have only 2 decimal places. So this means that now decimal points, drop off these guys. Drop off this one. And what will you do to the to this 9? 9 is raised by 1. Okay, plus 1. So this becomes
70.
So this is 83.70. 83. .70. Drop these off. Okay, so this is going to be these many milligrams is your answer. So yeah, some ambiguity is introduced in the final answer also, because you know you're rounding up or you're just bringing in those decimal points, but it is very little in when it comes to matter, you know, it's very little.
Can I ask a quick question?
Yeah, go ahead.
So in the 0.00056, I understand that's 5 decimal places, but in
Yeah.
the term of significant figures, is it 2 significant figures?
No, anytime
No,
you decimals, anytime
it counts at all. Okay,
it counts all this decimal.
all of it.
Yeah. So
Wait,
it's
not for significant figures. For significant figures, it's only the 5 and 6, right?
Based on the previous example, I thought it was 2.
1 minute. Let me just see.
Okay.
We have the 0.
Like there, you see, no, number 4.
Yeah, 1 minute.
64, 0 in front of the number not counted.
Not
So-
counted.
Yeah.
Not significant. Zeros in front of the number are not counted, not significant figures. Yeah.
So in that third one, that would only be 2 significant figures.
Is it because there's no actual number and it's just zeros and then it's the number, or is it like decimal then like an 8 and then the zeros? Is that why it's?
No, wait 1 second. So here we have these 2 zeros in front are not counting. Yeah. So yeah, no, you're right. The decimal points, whenever there's a decimal point here, these are not counted. These are not counting. So yeah, this would then be the 2 significant figures. If we remove these, if they are not like if you're, so from that perspective, yes, this is 2 decimal, yeah, 2 decimal points. And you know, even with that, so two places after the decimal. Yeah.
That's confusing. I understand the 2 significant figures. I thought you would still count all the decimal points because they're placeholders.
Yeah. Yeah, that is, see, and if you don't, then the addition doesn't work. You see that? If you don't count these zeros, then that doesn't work.
So I think this is just about decimal places, not about significant figures.
Yeah.
My understanding is the difference is if it's multiplication and division, then you use significant figures. But if it's addition and subtraction, then that's when you focus on how many spaces you have after the decimal point.
That's exactly what it is. And that's why where the confusion was when the student asked me, the student asked me, this should only be 2 significant figures. There was one student asked me, I don't know who it was, but so that's why it's, okay.
If you were looking at just that number, the 0.00056, not in addition, in an addition problem, then yes, it would be 2 significant figures. But because it's in an addition problem, that's when you have to look at the number of spaces away from the decimal point.
Right, yeah.
Okay.
But not, so yeah, I don't know. There was one student who asked me that. Who was, I don't know, who was that student?
This is Jana. I asked that question just because I was trying to clarify that with significant figures, just for a number like that, just to verify in my head that that's what it is.
Yeah, so that's, yeah, I know. And that threw me a little bit also, but here's the thing. Let's write it down so it's a little bit easier. Anytime you are adding numbers or you're numbers. So in that case, do not look at the significant figures. Look at the decimal points. Look at the decimal places or the decimal places. Okay? When you're acting, okay, somebody has a noise at the background, so I'll have to I don't like to mute students, but then that noise keeps disturbing. Okay, guys, so people know what's going on in their background, so please just mute yourself. That would be the best way to do it, okay? All right, so whenever you're adding and subtracting, focus only on the decimal places. Whenever you are multiplying, multiply and divide. In that case, you focus and you look at significant figures. Significant figures. So just focus on that part. If you bring the significant figures when you're adding and subtracting, then it doesn't work, because then the same situation is going to happen. Yes, 56 is a significant figure then, and these zeros don't hold any value. And so what happens is then you cannot add. So yes, like one of the students pointed out that these zeros hold importance. These zeros hold importance, all of these ones, and this one, and this one. In addition and subtraction also, okay? So these zeros, because they have a place value, they offer that place value. Otherwise, you can't add, you can't get the right answer. Okay?
What about in an algebraic equation where you have both addition, subtraction, and multiplication, division? If you have all those components, do you just default to significant figures?
Let's look at that one. I think in that case, PEMDAS will apply, you know. First, is there an example somewhere where you have two? Yeah, in that case, you know, the rule of PEMDAS will apply. You do the addition subtraction first. PEMDAS, multiplication and division first, then addition, and then last is a subtraction. I don't see an example here in the book, but that's what you need to follow. Okay? Follow.
Well, I mean for the final answer. So if you do an algebraic equation, like for example, density or something where it has all those components in it, the final answer will, I guess, probably look at significant figures and not the decimal places, right?
No, addition and subtraction. If there is addition and subtraction somewhere in that problem, then you do it. Yeah, you bring in the significant figures. Okay, let's do this one example here, which might help. If there is addition subtraction in the problem, right now I don't have an example here with me. Let's see. Okay, let's say if you are doing the density problem. So in the density problem, yeah, let's look at this density problem. Okay. Where there's no addition, but let's see. So density is mass over volume. Okay, mass is grams, weighed in grams, and the volume is liters. In the case of liquids, anytime you're measuring a liquid, how much space that liquid is occupying, that's in the liters, or centimeter cube if there is a solid. Okay, so that's for the solids. So these are the two. So let's say there's a thing called zinc. Zinc is an object. It's made up of this metal, zinc, an object made up of zinc, Z-I-N-C. Okay, so the weight, let's say these are some zinc beads, and the weight of these zinc beads come out to be 68.60 grams. And you measure the volume. Now, how do you measure the volume of these irregulars? So these are like little beads right here. How do you measure the volume? You put them in a cylinder. This is a measuring cylinder. And this has, these markings, and that tell you how many milliliters of the object is there. Okay, like a liquid is there. So Alicia Grant, this is page 50. Page 50. Okay, so here, so you fill this up with water first, and you note down the weight, like the volume in milliliters. So that is just plain water. So this is plain water. And now you add zinc pellets to it. These zinc is heavy. It settles down in the water. And then what is going to happen? Do you have any idea? When you drop the zinc, like little zinc pellets, what is going to happen to the water?
It displaces.
Yeah, or the level of the water
will increase. Yeah.
So the level of water goes up. So now the next level of water is actually the new volume, which comes after the zinc pellets have occupied their own space and they have displaced the water. So the amount of space that the zinc pellets occupy, that relate to the amount of water that is displaced. So here is the new water level, and now you note down. So you have the initial water, that is V1, you have the final volume, V2, and the volume that is found of the volume of the pellets is V2 minus V1. So whatever the volume is, that is the volume difference, is the zinc, the amount of volume that the zinc is occupying, the zinc pellets. Now, this is how you obtain the volume. And volume is what? What is volume? How do you find volume? Volume is the amount of space an object occupies. Space an object occupies. Okay, and milliliters is for the liquids, but milliliters and centimeter cubes are also interchangeably used. It means the same. Okay, so here is your zinc. The weight of the zinc comes out to be 68.60 grams, which you weigh on a machine, right? So this is one piece. This is the mass. And the volume is coming out to be 9.5 milliliters. This is the volume. All right, this is the volume. Now, when we call density, density is a formula, and density is mass over volume. So the mass is 68.60 grams, and the volume is 9.5 milliliters. So you divide it now. Now remember, anytime you have division, so division or multiplication, what do for the significant figures? You look at the lowest significant figure. So here the lowest significant figure is how much?
2.
2. Very good. So these are 2 significant figures. Two significant figures. And these are 4 significant figures. So what should be your final answer? 2 significant figures.
2.
Yeah.
That's about 7.2 grams per liter.
So this comes out to be 7 point. Is it like full 7.2 or something else?
Just
Okay.
7.2210.
Okay, 7.2210. So this is what you see on the calculator. But since you only need 2 significant figures, so you will stop here. So remember, when you do the decimals, you don't, those place values, these can be dropped. These are not counted. Okay, so here is 7.2 grams per milliliter. And this is the density of zinc. So this is how you do it if this is given in an example. Now let's look at one more example.
Professor, do you mind scrolling to the top of that page real quick where you wrote above that, the mass grams per centimeter? Okay, thank you.
Oh, grams per centimeter cube.
What does that mean up top there when you wrote those out? So I understand the density equation, grams per liter for liquid. Oh, that's just how you write in units?
Yeah,
grams
these are,
okay.
Grams per liters can also be written as G over grams per liters or grams per milliliters. They're commonly it's milliliters actually, but grams per liters also. Grams per milliliters and then grams per centimeter cube. So if you are measuring, if you're looking like if the object is a liquid, let's say finding the density of, let's say, Coke. So in that case, it would be grams per milliliter. But if you say find a density of a ring, of a silver ring you have, so that is a solid, so that's centimeter cube. That can be used as centimeter cube. But these are interchangeable also. You will see that. So it's the centimeter cube and milliliters is the same thing. I mean, and again, for regular objects that are regular objects, the one in which you can use the like a measuring what is it called, like a ruler, then length, width and height, that is the volume of a solid, right? But then irregular solids are measured this way, the way I'm sure through this method. So this is measuring the volume of the irregular solids. So yeah, it depends how the ring can be measured. The volume of the ring can be measured this way through this method of displacement method. This is displacement method. Okay, displacing the water, finding out how much water was displaced, or what is the difference in the water, initial volume and the final volume. So that gives you for the volume of the irregular solids. Okay. All right, so let's look at one more example. And let's see if we can get this using the significant figures. Using the percentage as a conversion factor. Okay, yeah, let's look at this. All right, here, this one is in a proper, like it's in a long problem here. Page 47, and this is a study check 2.12. Okay. Now here they're saying an uncooked lean ground beef can contain up to 22% fat by mass. So 22% fat by mass. Okay, and is present in an uncooked lean beef. Okay, how many grams of fat would be contained in 0.25 pounds? 0.25 pounds of beef. Okay, and the question is asking how many grams? How many grams of fat is present in 0.25 pounds of beef? Okay, so how would we do this? Clearly, we are looking at the relationship between pounds and grams. All right. So this is one piece. So we need to look at if there is a direct relationship that exists between pounds and grams. So let us see by pounds and kilograms is there. Pounds and kilograms.
I think 1 pound is equal to 454 grams.
Okay, 1 pound is equal to 454 grams. Okay, this is good. This is one piece. So get this equality from the tables, or we will provide you. Okay, this is one thing. Second thing is 22% fat by mass. Fat by mass means that 22, you can use grams over 22 grams of fat is present in 100 grams of the total, beef, mass of beef. Okay, this is what it means. So we are going to now, you can do it that way, or you can also do it 22 pounds of fat is present in 100 pounds of total beef, because percentages are like, they can apply to anything. Percentage can apply to any unit. Okay, so now start with 0.25 pounds of beef. First step, convert it into grams. Next, you use that percentage, factor, and from there you can get the grams of fat. So let's put this thing here. 1 pound is equal to 454 pounds, means 454 grams over 1 pound, or 1 pound over 454 grams. So these are the two conversion factors, just like you did the conversion factor for a percentage. So which one are we going to use? We want to get rid of the pounds and convert them to grams. So we are going to use this conversion factor. Okay, so now write down 0.25 pounds of beef, right? That's a ground beef, times, first convert this whole thing into grams. ground beef. So 1 pound of beef would be equal to 454 grams of beef. So this piece converts the pounds to grams. Next, we need the grams of fat. So we know that 22. So now we are going to take this conversion factor because we want to get rid of the grams of beef and we want the grams of fat. So grams of fat is on the top. 100 grams of beef is at the bottom. So now look at how they cancel out. Pounds of beef and pounds of beef cancel out. Grams of beef and grams of beef cancel out. And you're just left with the grams of fat. Next question is about the significant figures. How many significant figures here?
2.
How many significant figures here? Variable. So this is variable. So don't count this. I mean, it's okay to know that this is 3. This one is 1 significant figure, but it's variable. I mean, for 1, you just eliminate it. Now this one is again an exact number. So again, variable. This one is again an exact number, variable. So in any case now, because you have all these exact numbers with variable significant figures, and you know for sure that this is 2 significant figures, this is 2 significant figures. The 0 in front does not count. So what should be your answer in? Final answer should be?
25 grams of fat.
Yeah.
Because 24.97 is what the answer did, but we need to get 2 figures, so 25.
Yeah, 2 sig figs. Okay, so now you just do 0.25 times 454 times 22 divided by 1 times 100. So the answer is 25. Let's see.
Yeah, approximately. It's, yeah.
0.25 times 454 times 22, and that comes to be 2497. Divide by 100. So this comes out to be 24.97. Okay, so the answer, your answer should be in 2 significant figure according to the rules. 2 significant figures. So we need to make this into a 2 significant figure. So 9 plus 1, you know, so that 9 is dropped. 9 is more than 5, and this is 1 is added here. So this becomes 25 grams of fat is present in that beef amount, 0.25 pounds of beef. Okay, so that is your final answer. Okay, got it, guys? Any questions so far? So yeah, if I see a question that relates to like addition and subtraction, multiplication, all that's coming up together, then just do the PEMDAS. Yeah, these are all multiplication ones. Okay, let's do the last one using the density. Okay, the last one is here. Okay, this problem study check. So this is page 52. And here you have study check 2.13. Okay. Okay. During a surgery, a patient receives 3.0 pints of blood. Okay. How many kilograms? How many kilograms of blood? The density of the blood given is 1.06 grams per milliliter is needed for the transfusion. Okay, so look at these few things here. Pints, kilograms, and grams. You see that? Okay, that's one thing. Next is look at the density. Density, this whole density, it also means 1.06 grams is equal to 1 ml. Okay, and the conversion factors are 1 ml over 1.06 grams and 1.06 grams over 1 ml. All right, so two conversion factors. Now, let us get this. Kilograms is the unit of what? What is a kilograms unit of?
Mass.
Mass. And what is a pint a unit of?
Volume.
Very good. So pint is volume and kilograms is mass, so there's no direct conversion. The only conversion is through the density. So they are only connected through the density. Okay, so first step would be look at the relationship between convert pint to milliliters. Okay, convert pints to milliliters first, or in other words, convert the pints to milliliters, and then from milliliters to grams, and then from grams to kilograms. So remember, this is metric system. So this is 1 kilogram, METRIC. So in the metric system, 1 kilogram is equal to how many grams? Kilo stands for what?
1,000.
1,000.
1,000. Very good. So here's your 1,000. So this is kind of known. Next thing is the milliliters to grams. That can through.
I'm sorry, Professor. Can you please little bit lower it down? I just missed. Thank you.
So milliliters to grams, and that can only happen through the density, because milliliters is volume and density is mass, and so they can only go through the formula mass to volume. That's one thing. And the last piece is the pints, the relationship between pints and milliliters. So how many pints is how many milliliters, or what is that relationship? Let's see, there is a direct relationship between the two.
One pint is 437 milliliters.
Very good. So one pint is 473 milliliters. Okay, good. 1 pint is equal to 473 milliliters. You see that? When you go buy food, you know, all these units are written there. 1 pint is 473 milliliters. So we are given 3 pints. Convert that to milliliters. First, convert 3 pints to milliliters. So 3 pints times, we need milliliters on the top. We want to convert the pints to milliliters. So we know that 1 pint is equal to 473 milliliters, right? So this cancels out the pints, and now we are left only with the milliliter. So what do you get here? 3 times 433. How much is that? It should be an exact number.
Should be 473 actually.
Yeah, is it 473 times 3 instead of 433?
Yeah. 473, sorry. 473. Okay, yeah. 473 times 3 is how much?
1,419 milliliters.
1,419 milliliters.
Correct.
Very good. Okay. Next is we are going to convert this milliliters to grams, and that's using the density formula. So the density is 1.06 grams. So 1,4 milliliters times 1.06 grams over 1 milliliter. Grams per milliliter is what it means. So this piece right here is the density formula. Okay. Next is, what do you get here? 1419 times 1.06.
$15,504.14.
1,500 and
4.14.
1.4. Okay, good. Okay, now here's something important. Remember the rule. When you are multiplying, you are going, so this is variable again. It's the exact number. So leave it. I'm going to just put it EX number. This is again the EX number, so it's not counted. But how many digits are these? 3 significant figures. All right. So this whole thing needs to be converted to 3 significant figures. Now, if you start doing that, you are going to introduce some error right here in the middle. So error is introduced if you apply a rounding up or down rules. Therefore, leave as is for now. Okay. Now we will just look at it again. Now we have 1,504.14, and this is the grams. This is the grams. So we need to convert that to kilograms. So grams times kilograms. 1 kilogram, 1,000 grams, right? 1 kilogram is equal to, we'd already looked at it right here. Where was it? When I said that it's the SI unit. I don't remember now. Where did I put it? Yeah, metric system right here. So 1,000 grams is equal to 1 kilogram. Again, this thing. So now that's what we brought here. So here the grams and grams cancel out and you're left with kilograms. So now you will have 1,504.14 times 1 divided by 1,000. What do you get now?
1.5014 kilograms, I mean.
Say that again.
1.50414 because we're leaving it as is, so 414.
Yeah, 1.50414. This is what you.
That's what I said. Yeah, in kilograms.
Yeah, and this is no. Once again, and this is what you see on the calculator, but in the middle, you know, like I said, leave as is in between the steps.
Between.
Yeah, in between the steps. But final answer, we have to do something. So like here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 significant figures. Okay, and exact numbers 1, 2, 3, 4. These are 4 significant figures. But for the, 2 significant figures generally, 2, or in other words, 2, this should be okay. 2, if in that situation, when something like that happens, then just leave 2 places after the decimal. 2 places after the decimal. Okay, so this becomes, ideally, it is 1.50 kilograms. This is more exact. Okay, but you can, because see, the reason why I'm saying is here, there are 3 types of kilograms is what? It's a weight, right? You take the weight. There are 3 types of weighing machines. And you know, it's like, it's hard, I can understand, because the labs are not, you know, in place. So you could have easily just gone in the lab and see the 3 weighing machines. But 3 types of weighing machines, ones which are not so exact, are going to have only one place after the decimal reading. These are called a decigram balance. Decigram balance. So you will see only one place after the decimal reading on it. The other one is a little bit more exact. It gives you 2 places after the decimal, right? So 2 places after the decimal. So if you were to weigh something on it, you would see 2 places after the decimal. So this is the centigram balance. And again, when you weigh, you would see that 2 places on this machine. There is another machine which is more exact, 1.001. So this is called a milligram balance. So very, very like more precise, 3 places after the decimal. So in that case, yeah, the answer in this case, if you were to weigh, you are going to see 1.5 grams. In this case, if you take the weight, you're going to see 1.50 kilograms, sorry. And then on the other one, if you see 1.50, what was that? 4 kilograms. You see that? So which one is more exact? The last one, right? So in that case, you know, from that perspective, you know, we have to keep that in mind, you know, that. So generally that, like I said, common practices to just have 2 places after the decimal, because this is more commonly used decimal, more commonly used machine in the lab. Okay. Okay. Yeah, so this finishes, yeah, I know you guys want to take a break, and this finishes the chapter also. So it's 3:33, and your next chapter is on the matter, and let's take about 10 minutes break, 10 minutes. 3:33 is here. Let's just get back to 3:45, okay, 3:45.